Hello, today we will talk about modeling transformation. These are the today class objectives. So I hope that at the end of this lecture material, you can understand some of the class called data process step, which is also known as this rendering pipeline for rendering these triangles. And then throughout this the rendering pipeline, there are lots of these transformations, including the 3D translation, rotation as part of the modeling transformation. So we'll talk about them. Also, before we moving on to the today lecture material, last time we talked about this difference between point and vector. Also, we talked about this affine frame. Also, we talked about what are the actual different transformation representation in the local frame, also this global frame. Okay, so here actually I'm showing some of the schematic view of the classical rendering pipeline. Basically, we just defined some of the triangle on top of this kind of the rendering pipeline. So we provide a triangle on top of this pipeline, and then in the end, we actually getting some sort of the pixel, some sort of the color at each pixel coming out of this rendering pipeline. And then we actually typically have multiple steps. That's why we call it this rendering pipeline. We typically start with some of the 3D models defined in each modeling steps. For example, we define this cow and this each own modeling space where we are showing the x, y, z coordinate. We also showing this kind of another object and so on. And then we actually we perform these different different models into the canonical common coordinate frame. Typically, we call it this world space. So in other words, we somehow we define this kind of scene or the world, and then we define all object, light, and even this camera in this world space. And then sometimes actually some of the we also define the camera, but also we can perform some of the trivial rejection, which actually cannot be possibly seen from the camera. So as some of the optimization. And then also at each vertex of triangle, also we can illuminate some sort of illuminate, in other words, compute color for the potentially visible objects. And then we will talk about some of the technique how we can actually compute the color depending on the object orientation or the property of the triangle, also the other materials. And then also now here we define the camera. And then our goal is that we map this point defined in the world space into this camera space, and then this is also known as this viewing transformation. So then, if we do that kind of the viewing transformation, basically we actually transform this world vertex. In this case, maybe the teapot object into some another coordinate space in this image space. And then also we can do this kind of the clip object, which actually which are located outside this view volume. Actually they're given this camera. This actually the region that we can see. We call it this actual view volume. Also we actually flatten this 3D model into this image space, right? That's also known as this projection. So we actually project the 3D object into this 2D image space. That's actually some of the operations of clipping and projections. And then once we do the projection, then the triangle mapping to this kind of the image space, and here this little dot actually center of each pixel. Then we rasterize this kind of the triangle into the sum of pixel. For example, the simple idea is that if some of the center pixels are within this triangle, we give the color. We actually transfer color of this triangle into that pixel. That's the kind of the main idea of this rasterization. And then once we do that, we show this kind of the color of this pixel stored in the frame buffer into display. So as you can see, a lot of steps in the render pipeline actually require some of the change of the coordinate, right? So that's why actually I'm talking about different techniques of the transformation, since this is actually one of the core operations of this rendering pipeline of also the many graphics applications. So actually here I'm showing this kind of architectural overview of the GPU. Actually the Fermi architecture around 2010, more than 10 years ago. You can see that actually let me show this one. If we zoom this one, this is actually the kind of the GPU core. GPU core is not like the CPU core, but actually in the GPU core we can do some sort of the multiplication addition between vector. since actually basically you can just treat that this core actually the kind of the highly the dedicated some sort of process unit for perform the matrix vector operations. So basically when you perform this kind of the transformation, Ewing transformation and other one, it's nothing but the kind of the perform the matrix vector operations. And then also there are, so we also have this kind of the cache and some scheduler to enable this kind of parallel processing unit and other this part. But actually this actually the architectural overview of the GPU around more than 10 years ago. You can see that there are a lot of these parallel unit, highly parallelable. Also it supports this wide memory bandwidth. So you might heard about it recently, this HBM kind of very kind of hot topic recently, to provide this lots of data from the memory side to GPU. Also, it supports this CUDA, the general language, to run some sort of program within the GPU. And this actually I got this NVIDIA Hopper architecture, one of some of the recent this GPU architecture. As you can see, this little one now actually mapping to this kind of one. From the architecture, there are about 16 units like this. But you can see there are lots of that kind of unit, right? So in this kind of the Hopper architecture, there are about 18,000 the FP32 core. So basically, this the green box is actually FP32. Basically, this is actually kind of the single pre 32-bit. I guess it's the single pre 32-bit floating point operations. So you can see that there are a lot of cores. So that's why we actually when you perform this kind of random pipeline, there are so many triangles, so many vertices, right? But when you rasterize different triangles, also when you transform the different vertices, we can actually perform that kind of transformation in a parallel way, right? Then you can do that kind of transformation in a parallel way using this kind of many GPUs. So here also when you're doing this kind of the rasterization, also later on I will talk about the parallel algorithm of the rasterizing triangle into the pixel color. So then we can actually run that algorithm in a parallel way using the GPU architecture. And as you can see, there are lots of many parallel core which can run this kind of the different transformation in a very fast way. And then also we can use this kind of one for the recent this deep learning architecture, which also run this many matrix vector operations. So let me also briefly show some of this is actually the CPU chip. This is actually Intel Core i7 processor about 4 years ago. Also this one of it's just 4 years ago, but there are only a few core. Like in this case, actually about 4 core. But you can see that each core actually has a much more complicated. It takes more larger chip area, right? So each chip also it has its own memory, its own this L1, L2 caches. Also they support lots of actually complicated instructions. Also this is actually showing the L3 cache. So actually there are different actually different actually perspective to run the algorithm on the CPU and GPU. In the GPU case, we actually having the very kind of simple core, but that only perform the kind of the matrix vector operation. But as you can see, the CPU chips actually we can also support a lot of the menu operation like that is if then else, that kind of conditional branch and so on. Also, this actually I just got it. This Intel i9 chip actually the diagram, which are actually one of the expensive one, but there are the different core like a P core, E core. I don't know much about what are the main difference between P core. P core it's more about this powerful operations, and I guess E core is more the power efficient operation. So depending on actually some of the operation instruction application, also they can actually apply this different set of the core. But as you can see, there are compared to the GPU, it actually has a much less core. That's why actually the Intel chips are lagging behind in terms of supporting this recent deep learning the applications. Anyway, so basically GPU evolved in a way to enable this kind of the rendering pipeline a lot, where we have many of these the parallel units of the running transformation, which is nothing but matrix vector operations. That's the key driving force that actually differentiated over the CPU. Okay, so before we talked about some of transformation, I'd like to talk about some of the basic vector operations. Last time we talked about simple vector addition and multiplication, but also you might also we'll talk about the dot product, also the cross product operation, which are actually very commonly used in many of the graphics application. So actually, this is a dot product. This is actually the matrix representation. But as you know, the dot product between two vectors actually returns scalar value. But the much more important thing is that actually we need to have this kind of the geometric interpretation. So suppose that we have two vector, A vector, B vector, and then typically if we do this dot product, like this one representation, another one is that this another representation of dot product. Also we multiply the magnitude of each vector A and B, and then we measure the cosine theta. Theta is basically the angle between two vectors, right? Then basically this actually essentially given this the B vector A vector, if we perform the dot product between two vector, then actually we compute the magnitude, and then we project this vector on top of the A vector, right? And then actually we multiplying this one. So in other words, the ranks of the vector B project onto this another vector, right? Also we can also have another interpretation from the A vector to the B vector, right? And also if we treat this one as a point, the point B, then basically we actually computing the distance from here when you actually project that direction into the direction of this A vector. We actually project this distance into there. That's kind of the geometric interpretation. But actually, we commonly we are also when you do when you go over some of the graphics application, we commonly use dot product between two vectors. But actually, this is a kind of you should know as some of the simple geometric interpretation, which we commonly use for the graphics applications. And also, we can perform this cross product between two vectors A and B. Then this also it's a little complicated, but basically the cross product return another vector C vector that is perpendicular to this both of the A and B. And then basically this actually the simple geometric interpretation. If you perform the cross product between A and B, just wrap around the A vector, starting from A vector to B vector, and then your sum indicating this C vector, which are perpendicular to the two input vector A and B. And also this actually another way the same thing. Also we can define this cross product in that way, but here actually this based on this we can more easily actually memorize this equation. So given this one, we actually have this equation, but then if we take the this I, J, K, this actually canonical vector, this one xy like the x, y, z vector, then we set up these three components of A vector and another three components of B vector. Then first we take out this component, we pick this one, we take it out this row, also this this column. Then we actually multiply this one, AY, BG, and then take the minus of AG and BY with this I vector, and then we keep doing that. This one we take it out, this one, that one, then AG, and then we do this one AG with the BX here minus with the AX BY with the multiply with the J vector and so on. Then we can compute this cross product. This is actually the algebraic the equation, but the simple geometric interpretation. Also, okay, so basically based on this some of the information, we can also define some of the modeling transformation. A lot of cases actually we need to perform this modeling transformation. In the end, as I mentioned before, every single object actually defined in each modeling space, right? So we define this cow in each modeling space like this x, y, z, and then we actually to define the 3D scene, we somehow transform them, right? That's to locate this some of each model into within the model, right? That's the modeling transformation. And as we mentioned before, that basically there are two different actually interpretation. suppose that some of the model actually some of the model defined in each is modeling coordinate modeling space with the coordinate of C. Then if we perform the modeling transformation like that M here, then if we apply we can apply this modeling transformation M to the C within the same frame. And then also the another one is that we can actually we can apply this M with its own modeling coordinate into the another frame. So basically here actually given the global frame we change the coordinate, but also here actually we can modify this frame as a local coordinate. So suppose that some of the translation operation as an amount of tx, ty, tg, and then we apply the transformation into this model. Here actually we apply this t into each coordinate like this. Then we change the coordinate. This is actually one interpretation. Or we can actually merge. We can perform the matrix of multiplication, and then we define another frame. Then it means that actually we modify this frame. Basically, this is actually two equivalent interpretation of this modeling operations. Actually, we will talk about I will show some of the application of this concept later on. So now I'd like to talk about these three rotations. Three rotations are a bit complicated than the 2D simple rotation. I mean, we can actually in the 2D plane it's very simple to perform this kind of 2D rotation. But in the 3D space, actually, we can rotate this object along the canonical axis like x, y, and z. But since also we can rotate this object along the arbitrary this axis. Suppose that I want to rotate this one along this one, right? So basically, this happens very commonly in the computer graphics application. Suppose that actually I want to rotate it. So here actually I define my camera here. Then I want to rotate this object along my viewing direction, right? Then actually this is very commonly appearing in these cases. So that's why actually we need to perform this operation. There are many different approaches. We can actually actually at the high school or some long time ago you might learn that we can actually perform this kind of arbitrary rotation by using utilizing three canonical rotation, but it's complicated. But there's a lot of cases also we can do that actually with the cotton iron. I will briefly touch on this cotton iron. Here I will talk about I will actually talk about rotation based on this kind of based on the concept of the frame that we talked about last time. Okay, so before we moving on, we need to talk about some of the geometric rotation. Suppose that here I actually have the sum of vector x vector. Now I want to rotate this x vector along the rotation axis. Here actually the a head back another vector rotation vector axis the a. This rotation axis also the head actually indicating that this actually normalized one. Then actually if I rotate this object along this axis, then you can see that actually this vector rotate like this. And then here I define another two vector to define some sort of this rotation the frame. So out of these two vector we can define basically to define the frame we need to have the three orthogonal vector, right? And then if we take the cross product between a and x vector, then if we actually wrap this a and x, then we can have this kind of another vector. Then for this one, this actually the perpendicular this actually we want to compute this vector, which actually is also going to the a and that vector. But actually to compute this one, we flatten this x vector. Basically we flatten this vector along within this frame of that to the plane that's spanned by this vector and that vector. To do that, actually we cancel we flatten that component which actually located in the direction of a vector. I will give the information here. Okay, so given this the rotation vector a and given this input vector x, we can compute this. We actually compute this vector by taking the cross product between a and x. For this one, how can you compute this one? So basically, this vector nothing but we flatten this x vector by taking out this corresponding component of x vector along the a. If we take out this part, then this vector will be flattened to there, right? So this is actually the x orthogonal vector, which is actually computed by x minus the x. I will call it x parallel. X parallel vector is nothing but basically the a vector, which is actually a vector. But here actually we perform the dot product between x and vector a, which is nothing but if we take the dot product, then we actually project this vector onto there. Then basically this x parallel vector is this vector. If we take this component from the x, this is nothing but x minus with this vector. Then this vector flattened to this here. Then we can know that actually this vector will be parallel to the a, and then by definition also these two vectors will be the parallel to the there. There are some other information. I will skip this one. Also, when I skip this one, I'm not going to make any questions onto the skipped part, omitted part. So that's why you need to watch so to check whether you watch this YouTube video or not. I will some portion I will skip this one, but I'm not going to make any question on any of these midterm question on those part here. So this tensor product we can define this one. For this one, we need to use tensor product, but we can skip this one. Also, we can skip this one, another one. But if we we can perform that rotation with a very simple, by utilizing this concept of the frame. So again, same notation, a vector. This cross product, I will call this b vector, which is actually we can compute this vector with a cross product between a and x. This is actually x orthogonal vector. This is actually the input x vector. So then, by definition, these three vector, a vector, b vector, this x orthogonal vector, actually there are three orthogonal vector, and then we can actually assume that this may be the basic vector. Or if we take the normal line, we can actually treat as the three basic vector define this frame. Then we can actually define this frame with a vector, this vector, another b vector here with some sort of arbitrary origin. And then given this frame, we can represent this x vector within this frame, right? How can you do that? If we take another cross product, the dot product x vector onto the a, then we can compute this actually coordinate along this a vector. Then this vector has the coordinate of s along onto that direction. If we do the same thing, then it can have the t coordinate. If we take the cross dot product between this vector and that vector, and then obviously we know that that component will be the 0, and then also here we just treat it. I mean, we can treat it as the vector, but in this case, actually, we treat it as a point. Then this actually we represent this point with this frame, this affine frame. Then if we performing the rotation here, we want to rotate it here along the a vector, right? Then we can actually perform the canonical rotation matrix along this x that axis, which is actually the canonical rotation matrix in the 3D, which is nothing but this is nothing but like this. With basically we maintain the rotating along the x direction. So then x should be the maintained here. Then this is my cosine, minus sine, and sine, and 0, 0, 0, 1, 1, 1, something like that. Yeah, this is might be this actual rotation matrix along this canonical space. Also, actually, if you want to know more details about this part, I recommend you to look up my textbook. The textbook has more detailed information. Intuitive interpretation here is that actually by taking this component doesn't change, right? So you can see that that component, this one actually, this coordinate, when you do the rotation, this actually keeps staying during the rotation. Okay, so I'm not going to talk of this. Actually, the one simple the rotation technique using the affine transformations. Also, a lot of also the game engine also using this cotton ion. But actually, this also based on the complex number, it's a little complicated. So I'm not going to talk about these low-level details. But its main idea is that cotton ion actually directly supporting the rotation along the arbitrary rotation axis, in this case v, as an amount of the t. So this actually some of the actually this notation, some other information, but I'm not going to talk about these low-level details. Also, basically, we can actually perform the conversion between cotton ion to the rotation matrix. Basically, this actually the rotation matrix that we compute. We actually compute this actual this part is rotation matrix. Therefore, enabling rotation along this arbitrary vector. Also, even though I didn't talk about the low-level details, there are some sort of the relationship between the rotation matrix with cotton ion. But I'd like to talk about the cotton ion actually has useful information, useful advantage. It is actually turns out it is a more efficient, readable way to generate arbitrary rotation. In the end, once we understand the cotton ion, it's the much more intuitive operation, right? Given cotton ion direct support the given the arbitrary rotation as an amount of this t, we can compute this kind of the cotton ion representation. Obviously, that will be the more intuitive than this kind of approach. And also it turns out that also the cotton ion provide a numerically more stable than this 4x4 the rotation matrix. That's actually the cotton ion also very commonly used in many of these graphics, also robotic application. But in this class, I mainly talk about the rotation through with this affine transformation. If you're interested, I recommend you to look up some of techniques of cotton ion. And this actually the next homework in performing simple animation transformation. Let me briefly running this demo. If we run this demo, basically here, so it doesn't support too much, but actually when I click left button right, but it doesn't do anything, but it's showing some of it replace something. But if I rotate it here, it actually rotates my cow in its own modeling axis here. Actually, this red arrow, this is actually showing its local frame, its local modeling frame. If I click R, it actually rotating this one along this arbitrary created white vector, and then also if I do the X, it actually also translate along its own modeling space. X actually indicating corresponding to this red vector. If I click the Y, it also perform the translation along this y-axis of this its own modeling one. Like if I click the left button, if I change it, it actually translates like this. It's a very simple approach. Obviously, it's not that useful, but actually, I'd like to see what are the application of the modeling transformation that we talked about today into the simple graphics applications. So if you actually see its source code, also it actually use this approach, this kind of display list. Let me show if you see its source code, it actually using this kind of OpenGL command. It actually it somehow generate a list. Actually, this one, the display list. It's a group of the OpenGL commands stored for the later execution. Also, why we are doing this, it can be optimized in the graphics hardware. But actually, the recent OpenGL are supporting the vertex array object and other one. So this is actually much better one. But there also as a simple structure I'm using the display list. Also recent OpenGL doesn't use this one, but basically this is actually based on immediate mode. Obviously which is actually the slow. A lot of recent technique like the utilizing this kind of vertex array object actually they're for supporting much faster rendering performance using this retained mode. But anyway, I'm using this one since it's much more simple. So to create this display list, first I need to generate some of the ID, display list ID, GL general list with some of the, I generate only one the list, and then I define this new list by calling the GL new list, GL end list, and then I actually perform the drawing operation within this function by calling the define GL vertex and GL begin and end, that kind of one. And then when I using this display list, I just call this list GL list with this created ID. That's basically when you look up the source code of P8, you can see this one. But here these ones actually utilize this kind of display list. This has also some of the information, but actually some of the corresponding recent code. Instead of this display list, it actually using the vertex array object, vertex buffer object, and so on. Then if we do that, actually, it can support the much better performance. But it's a little complicated, so that's why actually I'm using this one. Okay, so again, today we talked about this random pipeline. Also, we talked about 3 rotation and some other informations. And then this is actually the regular homeworks. Watch the 2 SIGGRAPH Asia video or the paper, and then provide their summary. Go over the next lecture slide. If you have a question, also you can write down. You can submit your questions through this Google form link from our course homepage. And then next time, today actually we talk about modeling transformation. But typically we perform the lot of we do the lot of this camera related this transformation. That's called the viewing transformation. We'll talk about it next time. Okay, that's it. Bye.